Welcome, scientists. Let's just jump straight into it. Today, we're throwing on our imaginary lab coats and diving into the hidden chemistry of the everyday liquids literally sitting right in front of us. In this explainer, we're going to break down these complex household chemicals step by step. It's going to be a lot of fun.
Think about lemons, a bar of soap, or just plain old water. They look totally different, they taste different, and they feel different, right? But scientists actually group them using a kind of hidden color code. And by the end of our time today, you're going to master this exact spectrum so you can decode the invisible properties of pretty much everything in your house. So here's our game plan for this explainer. 1. The litmus indicator test. 2. Decoding the pH scale. 3 and 4 will hit everyday acids and bases. 5. Salts and neutral solutions. And finally, number 6, a real-world science quiz to test your chops. Let's get to it.
Okay, Section 1, the litmus indicator test. Testing unknowns safely.
Now, obviously, we never, ever taste unknown liquids to figure out what they are. I mean, that is a massive safety hazard. Instead, we rely on a super clever invention called a litmus indicator. Basically, it's this special paper that changes color to tell us if a solution is acidic, basic, or neutral. No tasting required, just straightforward observation. And here is the absolute golden rule you need to memorize. Blue litmus paper turns red in acids, and red litmus paper turns blue in bases. It honestly feels a bit like a magic trick, but it is 100% pure chemistry. Just remember, blue to red, acid. Red to blue, base.
Imagine actually doing this in a lab. You dip a blue strip into, say, vinegar, and boom, it turns red. You dip a red strip into a baking soda mixture and it immediately turns blue. But what about neutral solutions? Well, they won't change the color of either paper at all. It's essentially a foolproof system for classifying any liquid.
Moving right along to Section 2, the pH scale, measuring strength.
So, all those color changes map perfectly onto a number line from 0 to 14, which we call the pH scale. It doesn't just give us a simple acid or base label. It actually tells us exactly how strong that liquid really is. The lower you go down the scale, the stronger the acid. The higher you go, the stronger the base. It's that simple. And right smack dab in the middle of that scale is the magic number 7. This is your perfectly neutral solution territory. Think pure water. It's totally balanced, not acidic, not basic. It basically acts as the stable anchor point for the entire scale.
Section 3. Everyday acids. These are the liquids below pH 7.
You'd actually be surprised by how many of these acidic solutions are just chilling in your kitchen or even your school canteen. We're talking vinegar, that mouth-puckering calamansi juice, highly carbonated soft drinks, and yep, even tomato juice. They are literally everywhere. So, if you're taking mental notes here, these are your key clues for acids. They sit below a 7 on the pH scale, they famously turn blue litmus paper red, and in foods, they deliver that signature sour punch. But hey, a quick reminder, while food acids are totally safe to eat, strong industrial acids, those can be highly corrosive, so we always handle them with extreme care.
All right, Section 4, everyday bases. Now we're looking above pH 7. Bases are kind of the unsung heroes of daily life. They're really the backbone of hygiene. Your mild hand soap, the laundry detergent tackling grass stains, baking soda, and actually, the toothpaste you use every single morning, they're all bases.
How do you spot them in the wild? Well, unlike acids, bases clock in above a 7 on the pH scale, and they'll flip red litmus paper to a distinct blue. Also, if you touch them, like when you're lathering up your hands at the sink, they have this really recognizable slippery feel. That slippery nature is exactly what makes them so good at cutting through grease.
Section 5, salts and neutral solutions, the great balancers.
So what about the stuff that isn't acidic or basic? This is exactly where our neutral solutions and salts live. Picture ordinary table salt dissolved in water, the sterile saline solution in a hospital IV drip, or just the crisp mineral water you chug after gym class. None of them lean acidic and none of them lean basic. And this is exactly why that middle number 7 is so crucial. Neutral solutions sit right at 7. Because they're perfectly balanced, if you dip blue litmus paper in them, it just stays blue. Dip a red one, it stays completely red. Our chemical indicators are totally unbothered. Okay, Section 6, Real-World Science Quiz. Time to test your knowledge.
Let's set the scene. Mara is at her school canteen and decides to test some calamansi juice.
She dips a piece of blue litmus paper into her cup, and it instantly turns red. Okay, think back to our golden rules. How should she classify this? Is it an acid, a base, a salt, or water?
Lock in your guess. Next scenario, a group of learners are cleaning up after a science experiment. They dip red litmus paper into their soapy table cleaning solution, and boom, it turns blue. Based on that color change alone, what kind of solution are they dealing with?
Last one. We're at a Barangay Health Center, and learners are testing a standard 0.9% sodium chloride saline solution. They tried the red paper, then the blue paper, but absolutely nothing happens. No color change at all. What exactly do we have here?
All right, moment of truth. Because the calamansi turned the blue paper red, it's definitively an acid. That slippery soap solution flipped the red paper to blue, making it a solid cleaning base. And the unchanged saline? Yep, you guessed it. A perfectly neutral salt solution sitting right at a pH of 7. Awesome job if you nailed those.
You now have the fundamental tools to observe, test, and explain the physical world around you just by looking at a simple color change. So, next time you wash your hands, pop open a soda, or pour a glass of water, just think, what invisible chemistry is happening right in front of you? Thanks for tuning into this explainer, and definitely stay curious.